Hello, everybody. Recording is in progress. Welcome to our class today, February 9th, 2022. Our class today will talk about handout 5, which is context-free grammars. Sorry, I'm a bit sick, so last week we talked about pumping lemma and regular expression and non-deterministic finite automata, the relation between regular expression and deterministic and non-deterministic finite automata. And today we move to an upper level, which is wider than regular expressions and deterministic and non-deterministic finite automata, which called context-free grammar. I'll share my screen now to start the class. Can you see my screen? Thank you. At the beginning, before starting, is there any, I don't think so, but is there any volunteer question for this week or for this class from the previous class? I don't think so, but just to make sure. Is there any question? Seems no. Okay. So, handout 5 is talking about context-free grammar. And context-free languages and context-free languages. So, we prove using pumping lemma that certain languages are non-regular languages. So, recall our example in handout 4, which was the language L equal 0 to the power n, 1 to the power n, where n greater or equal to 0. We use the pumping lemma to prove L is not regular. That means there is no DFA, NFA, or regular expression that can describe it. Okay, then, so how do you describe it? How we can describe it? Guys, the transcript will I will freeze. It happened last term many times. So the thing, I can enable it, but because the number of participants and the length of the class, it will freeze somewhere. So sorry, I cannot accept it. So we use the pumping lemma to prove that L is not regular, but we cannot, or can we find a way that we can describe this language with a computation? We will see. So we are ready to graduate to a border class of languages. What do you mean we graduate? We will move from the first level that we talk about in languages without memory, which is deterministic finite automata, non-deterministic finite automata, regular languages, and regular expressions. We'll go to an upper level. That what we call it CFLs, or context-free languages, or context-free grammars. The set of regular language is a subset of the context-free languages. So context-free languages are a wider, a bigger scope that the first level we studied, which is the DFA, NFA, and regular languages and regular expression, are a subset of this context-free languages. So REG is a subset of CFL. That means if L belongs to regular, if L is a regular languages, then L belongs to CFL. Though as well, we will see there is exist languages M also belong to CFL. However, M is not regular. So non-regular languages could be a part of CFL. And this called Chomsky hierarchy. So we start with regular, which DFAs, NFAs, and regular expression. The upper level is context-free languages, CFGs, PDAs, push-down automata. We will see this later. Then context-sensitive languages, which is beyond our course scope for software engineering. Recursively enumerable languages, which is the Turing machine, which is part of our course. So only the context sensitive, it's beyond our scope in this course. Representing languages. If the language is regular, then automaton based, we will have a DFA and NFA and regular expression that describe that language. If it is context-free, we'll use push-down automaton, context-free grammar. The expression will be represented by context-free grammar. If it is a context-sensitive, linear bounded, which is not studied, we will not study this. Context-sensitive grammar will not study this. Recursively enumerable will study Turing machine, and there is the how we will express that language. Use unrestricted grammar, which is beyond our course scope. So, in the previous lectures, we studied deterministic finite automata, non-deterministic finite automata, and regular expression. This lecture, we will study context-free grammar, CFGs. Next lecture, we'll talk about push-down automata. Later lectures, we'll talk about Turing machine, then the complexity classes. Is that clear? How we'll go through the course. By the way, today's class, let me see the chat. Okay, good. Thank you, Gareth. Thank you, Tai. This handout 5 until class note 7 that we will study today and tomorrow. This is the midterm material. So handout 6, class note 8 is part of the final exam material, will not be a part of midterm. I'll send an announcement that what is the material of midterm, which is handout 1, 2, 3, 4, 5A, 5. And the pumping lemma study guide, it's available on OWL, which is connected to handout 4, and the class note 1 through 7. Clear? So till the end of tomorrow class is the midterm material. Grammar. And also this is the material of assignment 1. So if you see that assignment 1 will ask about context-free grammar also. Okay, grammar. What do we mean by grammar? Grammar is a set of rules governing the structure of a string, how we should write our string. In natural language, it describes how sentences are constructed. Now, in sentences, it is noun, phrase, verb, phrase. Noun, phrase, it's a complex noun, prep, phrase. Verb, phrase, it's a complex verb, prep, phrase. Prep, phrase, it's a prep dot complex noun, article noun, complex verb, verb or verb noun phrase. Article, it's a or the. Noun, it's like, these are example, boy, girl, flower. Verb, touch like flower, prep, with. So these are the common language grammar, how the sentence is formed in English. Let's build a sentence with this grammar. Noun, phrase, verb, complex noun, verb, phrase, article, noun, verb, phrase, a noun, verb, phrase, a boy, verb, phrase, a boy, complex verb, a boy, verb, a boy sees. Now, how we start with the set of variables and then we replace those variables with words or other variables. We keep going until all that left is words. We use the grammar to produce a valid sentence. So this is the grammar. We keep simplify it till we just write words that will form a sentence, or we have a valid sentence grammarly in English. So what is a context-free grammar? A context-free grammar is a formal grammar that describes the set of context-free languages. So CFG, it is a formal grammar that will describe a set of context-free languages. The definition of context-free grammar: a context-free grammar is a for tuple V, alphabet, sigma, R, and S. V, a finite set of variables. Sigma or alphabet, a finite set of terminals. R, a finite set of rules in which a variable may be replaced by some concatenation of variables and terminals. S belongs to V, a start variable. We will see. Definition 2, a context-free language. A language is context-free if and only if there is some context-free grammar that describes it. When we will call a language its context-free language, if there is a context-free grammar that describes that language. A context-free grammar is similar to regular expression. It's like recipes for producing a string. The set of all strings that can be produced or derived by this recipe constitute the language describe that grammar. So we'll put these terminals, these variables, till we arrive same as language, like a boy sees, the example we took. We will keep minimize it till we receive the thing that can describe that language, and then we'll call that. Since this context-free grammar describe that language, then L is a context-free language. The idea is you start the first variable from there. You can substitute variables for variables or terminals as per the production rules. When there is no more variable, you stop. So we have something that we'll see now. We call it production rules. We will see. Our first example. Our example that you are familiar with now, which is 0 to the power n, 1 to the power n, where n is greater or equal 0. We said that there is no DFA or an FA or regular expression can describe it, but watch how easy it is to describe with CFG, context-free grammar. We will start with A, which is, if you remember here, in the description, sometimes we use S, but you can use A, B, V, T, whatever you want. We start with A, then we said 0, A, 1, or epsilon. This is the context-free grammar that describes this language. The interpretation of this production rule is start with A, then any instance of A can be replaced with either epsilon or 0A1. Why 0A1? Because we said the number of zeros should equal number of ones. So let's see this grammar in action. Suppose we use this grammar to derive the string 000111, which is satisfy this language. So we start with A, then we say A is 0A1, the first rule or the first grammar. Then we will substitute the next 0 with another 0A1. Then we will replace the third 0 with the rule 0A111. Then we will replace this one with epsilon. Then it will be 00111. No more variables, so we stop. Clear or not till here? Questions? Okay. Now, one important application of CFGs is to compiler theory for programming languages in application of well-formed parentheses. For example, these parentheses. If we want to have something for these parentheses, is in the language of a well-formed parentheses, but this one is not, nor this one is not. So we will have the context-free grammar. Yes, Brandon. This is the rule we have. We have this rule 0A1 or epsilon. We don't have any other option. Later on in some example, we might have more. But for this example, each occurrence, we will replace it with 0A1 till we are done. Then we will replace the A with epsilon. Yeah, like a recursive call, yes. Okay, again, the interpretation of the production rule is start with S, then replace any instance of S with S in a balanced pair of brackets. SS split into two components. Epsilon is an empty string. So we replace it with this S or SS or epsilon. So previously we have only one production rule and epsilon. Here we might use the parentheses with S or SS and epsilon. So to replace this or to represent this, we start with S. We have the first parenthesis, then S parenthesis, then left S right parenthesis. Then we will replace S with SS to have the inner two. Then they will replace them. Then we will replace S with epsilon. Then we have no more variables, so we stop. Is that clear? That's why we have in the production rule the SS. So, third example. Let L string W contains more ones than zeros. Let's begin by considering the string that contains no zeros, because it said contains one more than zeros. What if I don't have zeros? Also, the condition is satisfied, so it could be without zeros. Will still need at least one. So it contains more ones than zero. So let's start off with that rule and then move on other variable. If we said st1t, now what should t be? Well, we let t to be replaced by epsilon, then we can terminate any t at any time, which it seems useful. So next, we need a rule that guarantees that at any time we add a zero, we also add at least one. So the next rule, it will be 0t1, 1t0, either. Next, we should have the ability to add arbitrary many additional ones. Then we can replace it with 1t. Finally, we need the ability to spawn more variables in order to make arbitrary combination of the above rules. Then we call it TT. Let's see. So our grammar looks like ST1T. T could be a TT, 1T, 0T1, 1T0 epsilon. And here we make sure that we have the first one, that any new zeros will keep less amount than ones. Try a few different derivations to convince yourself. There is no way for this grammar to produce a string with equal or more zeros than one, because we start with one here. We have one more at least. It can't produce any other string. Now, theorem 3, every regular language is a context-free grammar. Recurrent language is regular if and only if. This means if and only if. If we have if, that means it's if and only if. There exists some DFA that recognize it, and the language is context-free if and only if there exists some CFG that generates it. Therefore, to show every regular language is context-free, it is sufficient to show every DFA has an equivalent CFG. Let's see. To convert a DFA to CFG, all state QI belong to Q become a variable QI. All symbols S belong to alphabet become terminals. All transition QI times by S lead us to QJ becomes rule QI to SQJ. Start state Q naught belong to Q become the first rule Q0. All transition in an accept state QF belong to F become rules QF to epsilon. We will see. If we have this Q0, which is the start state, if we receive a 1, we'll back to Q0. So it will be 1 Q0. Or if we receive a 0, we'll go to Q1, it will become 0 Q1. Is that clear, guys? At Q1, if I receive a 1, I will stay at Q1, 1 Q1. If I receive a 0, I will go to Q2. In Q2, if I receive a 1, I will stay in Q2. Then to terminate, since it's a final state, then I will add the epsilon there. You see here the rules? It should lead to epsilon at the end. Is that clear? Questions? Questions, guys? Okay, so let's open the class notes. Can you see the class notes, guys? Okay, sounds good. Thank you, Alanji. Context-free grammar recognize a language, a larger class of languages than regular languages, application in a programming language and compiler design. Informal description, it consists of 4 components: terminal symbol similar to the alphabet symbols. Variable symbol can be replaced with a string of variables and terminals. Production rule dictate how variables get replaced. Then start variable, starting point of the computation. How computation happen? Write down the start variable as the current string. Pick a variable in the current string and replace it with one of its production rules. Continue step 2 until no more variables are left. So these are the steps. As an example, if we have, what do we mean by terminals? Like zeros and 1, variable like S or T or A, whatever you want. Production rules, these are the production rule. S will lead us to 0 as 1, S will lead us to epsilon. Start variable, we start with S. Note, variable are denoted with capital letters. Don't use a small letter to denote variables. Clear? Always capital letters. So S0 S1, then 00 S1 1. This is our example. Then 00 S1 1 1. Then 00 epsilon 1 1 1. Then we'll come to the example in our handout. For example, if you have W equals 0 to the power 5, 1 to the power 5, then we'll do S0 S1, 00 S1 1, 00 till we reach to the 5. Then we will replace it with epsilon, then we'll have 0 to the power 5, 1 to the power 5 here. Hence, W is acceptable by this grammar. Yes, you can combine, yes. What do you mean by combining? That to put here, no, you either replace it with the first one or the second one while you solve the question. Okay, every string of the form 0 to the power n, 1 to the power n, when n is greater, is accepted by the grammar. Does the grammar accept any other language? No. Yeah, you can write it in two different ones, or use the column which represent the or. The grammar accept the language 0 to the power n, 1 to the power 1, where n is greater or equal to 0. What is the language that accepted by this context-free grammar? Terminals that we have 0 and 1. Variables S or A or B. Production rule are S will lead us to A as B, S will lead to epsilon, A will be 0, B will be 1, 1. So start variable S will go to A as B. If we use A, it will be 0 as B. Then S will give us A as B again. S will lead to epsilon, then it will be 0 A epsilon B B. Then we will replace B with 1 1. Then it will be 0 A 1 1 B, then B 1 1. Then it will be A 1 1 1 1. A will lead to 0, it will be 0 0 1 1 1 1. The language accepted by this language is the 0 to the power n, 1 to the power 2n, where n is greater or equal 0. Clear? So either I give you the string here and you will derive the context-free grammar with the production rule and the variables, terminals, or I give you these things, terminal, variables, production rules, and I will ask you to end up with the language description. Clear till here? You see, this is easier than the pumping lemma. To me, it's clear. Since I give you these things, as you see, we start with it. We took any scenario you will take of these replacements at the beginning, then it will lead you to symbols of that alphabet. Then you see here it's 0 0 and 4 1s. So that means 0 to the power n, 1 to the power 2n, where n is greater or equal to 0. So these are the language. It's easy to describe it. You don't have to know, you have to derive, then you will find the answer. Clear, Timmy? Sounds good. Okay, if you have a language equal a to the power m, b to the power m, where m greater than 0 and m is in between n and 2n. It's more complicated example. There is, at the beginning, Brandon, from the definition, we said it has a finite set of variables and terminals. So we cannot go infinitely. But this example, if you choose here, for example, if you choose to terminate here, then you will have 0, 1, 1. It's clear. Why we add more? In order to have a clearer rule. From the beginning, once you look at it from here, that the number of zeros is half number of ones. It's clear from the definition. Why we make it 0, 0, 1, 1? Just to make sure. But you can't do it 0, 1, 1, and you end the string at there. Then you will say you'll end up with the same description of the language. Clear, Brandon? Yeah, guys, the key is here. What will lead you? Forget the epsilon. What will lead you to the final? A will be replaced with a 0, B will be replaced with 1, 1. Then I have, if the number of zeros is n, then the number of ones is 2n. I can just find the answer from here. Okay, so in this example, the number of A's would be n, and the number of B's is m. The trick is with m. M could be either equal to n or as maximum to n. Okay. From here, you will have the B's. It could be 1B, which is the equal number of A's, which is n, or it will be double of that, which is BB. So with this rule, and the first one is A, and the main one is A as B or epsilon. So with this one, it's very easy. Once you receive these things, just make sure where is m. It could be as minimum, same as A's, the number of B's, or as maximum 2, the double number of A's. Then the rule will be B or BB. That's it. Okay, let's have this language. W belongs to 0 and 1 star. Number of zeros in W equal number of ones in W, which is the same. If you back to the first example, it will lead to the same thing of this. But here we use it as a star. So W zeros and end of 1 equal number of zeros and 1, then it will be 0 as 1s, 1 0, 1 as 0 s, and epsilon. Here we make sure that the number of zeros and ones are equal, whatever we start with ones or zeros. And here's the production rule of this language. Language of the balanced parentheses. String over left and right parentheses. With this one, 1, 2, 2, 1, or like here 3, 3, or we start with parentheses, another parenthesis, another parenthesis. This one is wrong and this one is wrong. Same as the example in the handout. So we will say W belongs to left and right star. W is balanced, which means the number of right parentheses equal the number of left parentheses. S will lead to S or S epsilon. Then if we have this one, we'll end with this one or this one, and we end with the required one. Is that clear, guys? Any question till here? Okay. Now, regular languages, as we said in the handout, are context-free grammar. Let L be a regular language. For every, there exists a DFAD such that L equal L of D. Construct a CFG variable V RI QI belongs to Q. If the transition function QI and will lead us to A QJ, then add the rule RJ will take us to ARJ. If QI belongs to F, then add the rule QI to QI. Start a variable here with R0, same as in the handout here with those things. It is the same. Any question? Any question? Okay, I'll show you now the material of midterm exam. So here we have the class notes that we have till 8, but it is till 7. 8, I think, for next class. Yeah, push down automata is not part of the midterm. So till class note 7, here is the midterm material. And from the handout 1, 2, 3, 4, 5, 5A. And here, this one, some of you, they don't notice it. It's like a guide for pumping lemma. It's a guide to solve pumping lemma questions. So these are the material of the midterm, and for a class note, it is till class note number 7. 8 is not part of the midterm. Oh, I don't have.
Sir, we can't see the screen.
Okay, sorry. Again, guys, these are the class notes from 1 to 7 in the course resources. Let's back a level. And handout 1, 2, 3, 4, 5, and 5A. And here, there is a study guide for pumping lemma. It's like summarize the steps, how you can do your proof, the proof steps, example, how you can solve it. This is the study guide for pumping lemma. For the handout, only everything is in there, is in the midterm material. That's why I didn't add more handout. But for the class notes, it just till 7. Number 8 is not included in the midterm. It's for push down automata. Push down automata, we will start on it tomorrow. However, it's not part of a midterm material. Questions till here. And today's video, I will upload it right away. I hope that YouTube will take like almost 2-3 hours to upload it with HQ version. So I will upload it today, so you have the full midterm material. For pumping lemma, there are several ways to prove a language is non-regular. It depends on you what you will choose. Y to the power I, what you will choose I, and how you will split your string. These could be different, that each student have a different split than others. Each student, one use I equal 0. Some of them use I equal, I couldn't use I equal 0. I is greater than 0. I equal 1, I equal 2, I equal 3, I equal 10. It's your call. And how you split the string X, Y, and Z, it's also your call. So that's why we might have many different solutions. But all should lead that the language is regular or not regular. Clear, Favor? And guys, go to the textbook. There is so many examples for pumping lemma. I can show you some. Can you see the book? Yeah, here in page 67 in the book, which is the first book, Introduction to Theory of Computation, Anil and Michel, which is at the University of Ottawa. So here the pumping lemma start. They explain the same example that we have. Here another example, 0 to the power n is a prime. This is the proof application of pumping lemma, first example. That the same example we have before. The another example that we have, second example, third example, fourth, fifth, sixth, 7 examples are in there. For the pumping lemma, 8 example. It's 8 example till page 76. And also you could find, I'm not sure this book has questions or not. Sure. Yeah. So also pumping lemma. For example, this one, question about pumping lemma. Pumping lemma to prove that these are also questions that you can use pumping lemma. This is one of the trickiest questions. So also on page 86, there are a lot of examples that you can solve them for pumping lemma. Questions, guys? Our class today is short. I don't want it to go to the 6th handout, which is the push down automata. We'll go tomorrow using this. And tomorrow also we're back to pumping lemma, but in different ways. So that's why I need to spend like tomorrow's class and next Wednesday class talking about this topic, which is pumping lemma for context-free languages. And I don't want to put you under confusion to include both parts in midterm. So if you have a question, please ask. If you don't have, you are free to leave. See you tomorrow.
Have a good one.
You too. You too. Thank you.
Thank you.
Thank you, Favor. Thank you, Tai. Thank you, Longi. Thank you, Austin. Yeah, I'm starting to feel better, but still, I'm not sure. Tomorrow I have a COVID test to see if it's Omicron. I am not sure if I catch it. But everything is okay. Thank you, Austin, for asking. Do you have a question, Austin? Richard, do you have any question? Richard, are you there? See you tomorrow, guys. Have a good day. Bye for now.